The following program is video supplemental instruction. VSI is brought to you by the Teaching Center, UF's Learning Support Center, www.teachingcenter.ufl.edu.
Problem 13 states the rotational inertia of a uniform thin rod about its end is ml squared over 3, where m is the mass and L is the length. Such a rod is hung vertically from one end and set into small amplitude oscillation. If L equals 1 meter and m equals 200 grams, this rod will have the same period as a simple pendulum of length blank. Alright, so we're dealing with oscillations and pendulums, and one is given to us, it's just a rod pivoting about its end, and they tell us it has a length L equal to 1 meter and a mass m equal to 200 grams. Furthermore, they actually give us our rotational inertia value. They tell us that it has a rotational inertia of ml squared over 3, which is standard for a rod, but they make it so you don't have to actually know it, which is nice. So I is going to be equal to ml squared over 3. Now what we want is a simple pendulum, which is pretty much just a ball and string, that has a certain length to give it the same period, which I'm going to designate as a lowercase l. So we don't know what that is. So we wanted to compare the periods, so a good place to start with this is to look at the formulas for periods of different pendulums. Now, if you have a physical pendulum versus a simple pendulum, you definitely need a different formula, so don't use the same one. So the period for a physical pendulum is going to be 2 pi times the square root of I over mgh. Okay. Now, we're given I, we have our mass, we know our gravitational constant. Don't let this h trick you. Some people will go and say, well, h is just going to be equal to L, and it's not. H is equal to L in this, but h is actually going to be the measurement from the point of rotation to the center of mass of the pendulum, which for a uniform thin rod is going to be right smack dab in the middle, which is going to be actually L over 2. So we have to keep that in mind when we're calculating. H is going to be equal to our L over 2. Okay? So with that, my first step I think you should do is just to go ahead and start plugging in our variables, get rid of that I, get rid of that H, get everything in terms of basically L, M, and constants. So, reducing this a little bit, I'm going to plug in I and say, well, I is just going to be equal to our ml squared over 3, and then we have our mgh. Now I know this is a lowercase, that's how the formula is presented, but they gave it to us as a capital M, so I'm just going to keep using that. mg, and then don't forget our L over 2. Alright, so making this look a little bit nicer, we can rewrite this as 2 pi square root. This L cancels the square on that L. The m's actually end up canceling out. Our 2 is the denominator of a fraction in the denominator, so that moves up to the numerator. And we end up with 2L over 3G, where G is a gravitational constant. Now this is for the physical pendulum. What we need to do is we need to compare that to the simple pendulum. So the period for our simple pendulum is just going to be 2 pi square root of L over G, alright, which isn't too far off from that. So we want to figure out what L is in terms of capital L over here. So I'm just going to set them equal because we want the periods to be equal. That is how the problem is designed. We want this to be equal to this. Alright? So we can say that 2 pi root 2L over 3G is going to be equal to 2 pi root lowercase l over G. Now, from there we can cancel our 2 pi. There's a root g in both of them, and we can actually square the entire equation to get rid of that square root sign. What we end up with is 2/3 of L, our big L, for our physical pendulum is going to be equal to our lowercase l. Alright? So, just kind of moving over here past know our lowercase l is going to be equal to 2/3 of capital L, which was given to us as 1 meter. So that's just going to be 2/3 of a meter, or 66.666666 centimeters, which they give it to you as 67 centimeters. So, keys to this are just to recognize the fact that the physical pendulum and the simple pendulum, you have different formulas for it. Generally, the period doesn't matter. It doesn't matter how far you pull it back. The period for a pendulum is always going to be the same, and it basically depends on mass and length. And for a simple pendulum, just on length. And don't forget your h. H is going to be the distance from the pivot point to the center of mass, not necessarily the entire length of the pendulum. And that gives us our answer of 67 centimeters, number 1 on your practice test.
The Teaching Center, UF's Learning Support Center, www.teachingcenter.ufl.edu.